chapter, it's chapter 3 in your text, it's called Linear Filtering of Random Processing. Basically, how do I describe the output of a linear system given that its input is random? To do that, we're going to start off reviewing. We're going to write down some equations for deterministic signals, kind of a review of undergrad linear systems. How do I describe the output of a linear system given a deterministic input? Because those equations will be kind of showing up today and be good review once we do switch over to random signals. So let's just do a little bit of a review, and then we'll dive into linear operations on random signals. So the first one is going to be continuous time linear systems. Let's talk about some of those basics and some of the themes we need to be familiar with. So in terms of input, output, hopefully you remember how inputs and outputs are related. My output is a function of my input via convolution with the system impulse response h and the input x. So hopefully that convolution integral looks reasonably familiar. Here I have time reversed and shifted h. You could also write it equivalently as a time reversal and shifting of x. Right? Those are completely equivalent things. We kind of get tired of writing down this integral, so we actually give this a shorthand. We would call this h convolved with x. Right? We use that kind of star notation. This integral here we would say is x convolved with h. Convolution is commutative, doesn't matter which order you do it, you get the exact same answer. So that's what we call the convolution integral. Most of the time we have what we call an LTI system. It's linear time invariant, meaning my system isn't changing with time, so I only have a single impulse response. If I'm time variant, this integral looks just a little bit different. It looks like this. H of t comma tau, x of tau. Very similar, but I now have a two-dimensional h. If I'm time varying, I need to know the impulse response at any time. So tell me what the impulse is right now. Tell me what it is now. Tell me what it is now. It's possibly changing with time. This is called the superposition integral. Personally, I rarely deal with time varying systems. We're almost always up here, but it's kind of a nice thing to know. One important property of any system is it stable or not? And we have this concept of BIBO, stable, bounded input, bounded output. Basically, hey, when do I get a reasonable output given a reasonable input? And mathematically, we write that like this. If my input is bounded by some number for all time, so its magnitude is less than some constant m sub x. I had to make that look like a subscript very well, did I? M sub x. So if my input is bounded, if that implies, and that's what I mean by the arrow, so if I have a bounded input, if that implies that my output is also bounded, m sub y for all t, this is less than infinity, obviously, then we call it a BIBO stable system. So bounded input implies a bounded output. That's what we mean by a BIBO stable system. There was a nice check on that, if you remember, way back when, that I'm BIBO stable if and only if, so that's the double arrow, my impulse response is absolutely integrable. So if I have a linear system that has some impulse response h of t, I hand it to you, you take the magnitude, you add up that area underneath the curve, and you get out a number of 84,000. Okay, that's not infinity, so this is true. And this implies BIBO stable. It goes the other way too. If I tell you it's BIBO stable, you know that this integral is less than infinity. They're one and the same criteria. If I am time varying, this integral looks just a little bit different. You have to write it like this, minus infinity to infinity, h of t comma tau, take the magnitude, d tau, it has to be less than infinity for all t. So pick a t, do the integral. Pick another t, do the integral. If this is true for all t, then this time varying system is also Biot stable. So one more thing I want to do here, we can think of this in kind of a limiting sense. So let's come back up to this integral right here. Instead of going from minus infinity to infinity, let's call that output yn of t. Go from minus n h of t gamma tau. So I'm going back up to that superposition integral. I missed part of it though. Obviously, as n gets big, then this quantity turns into this integral I have up here. I just let the limit of the integral get large. So in the limit, this turns into y of t. But you got to be careful. Really, what is this integral? Really, an integral is the limit of a summation, right? It's our Riemann sum. So really, I can write yn of t itself as this limit. I'll just write this out. Goes to 0 of multiplied by delta tau, the sum k equals minus n delta tau, and over delta tau. So as delta tau is getting smaller and smaller and smaller, the number of things in my sum is getting bigger and bigger and bigger. I'm adding up smaller and smaller with rectangles. I have to query this at t multiples of my time increment. Sample each one of these functions of multiples of delta tau. I'm adding up those rectangular strips. In the limit, as this gets really small, this converges to that integral, right? It's just what we call a Riemann integral, Riemann sum. The most important thing here is words. Y of t is just the limit of a finite number of linear combinations of the input. And you can see that right here in this integral, right? I'm taking samples of the input, I'm weighting it by these numbers, adding it all up. That's what we call a linear combination, right? Grab all these things, multiply them by numbers, add them all up. That's what we call a linear combination. So here's my linear combination. My output y of t is just a limit of this linear combination of inputs. Not too surprised here. We know the output's a function of what comes in. We'll see this a few times today where, yeah, the output's just a limit of a finite number of linear combinations of the input. The words there are more important than tedious Riemann definition, really. All right, I'm okay with that. So real quick review, but hopefully things you're familiar with thinking about. In your convolution integrals, Biot stability, and then this is kind of a different thing, but we'll see that a few times today. Let's do the same thing just real quick for discrete time. Let's just jot down a few relevant things for discrete time as well. Discrete time. Very similar things. We have an input-output relationship. We say that the output y of k, n equals minus infinity to infinity, h of k minus n, x of n. That's what we call the convolution sum. You can also write it like this. N equals minus infinity x of k minus n, h of n. Right? Doesn't matter which order you do it. This I would call x convolved with h. That I would call h convolved with x. So very same notation even, right? Just the context tells you whether you're doing a summation or whether you're doing an integral, right? Here's continuous time. This is discrete time. So convolution sum is what describes inputs and outputs. The output is related to the input via the impulse response via this summation. If it was time varying, I have a different equation. It's very similar though. It's still just a sum. N equals minus infinity to infinity, h of k comma n, x of n. Here's that two-dimensional h again. So the same story with continuous time. For continuous time systems that are time varying, I need really an infinite collection of impulse responses. I need to know at every single time what the impulse response is right there. Same thing here for discrete time. I need to know at every single time what the impulse response is. This summation is called the superposition summation. We have the superposition integral, now we have a superposition summation. What about, so that was input output, what about stability? How do we know if things are stable? Very similar story, Bibo stability. If I have a bounded input, and that implies a bounded output, then we call it a Bibo stable system. The check is the exact same type of check. I take the impulse response, I take its absolute value, now I add it all up. If I am less than infinity, that implies that I'm a Bibo stable system. If I tell you that I'm a Bibo stable system, that implies that this summation is less than infinity. Previously, we called this quantity absolutely integrable, because I was integrating the absolute value. This we call absolutely summable. If you can take a signal, take its magnitude, add it up, and get a number less than infinity, we call that absolutely summable. If you look up here, very similar thing can happen again in terms of this limiting behavior. This one's even easier to see though, because I don't have to get rid of an integral. If I call yn of k, replace little n minus n to n, h of k comma n. So I'm going back up to that superposition summation. Look what happens. The limit as n gets big of yn of k equals y of k. So my output is just a limit of a finite number of linear combinations of the input again. Here's samples of my input, here's weights that weight it, I add it all up, that's called a linear combination. In the limit as n gets big, that's what my output is. So the exact same words that I wrote here, I can write here again as well. The output is just a limit of a finite number of linear combinations